Okay, so welcome to worksheet 12. We're doing again this virtual setup, so hopefully it all looks good on your end. We're going to be covering a lot of things, from that relativistic linear momentum all the way through that Bohr model. So like I said, we have the equations. Oh, I'm talking about the equations. Oh, dang it, I don't have it here. But you guys have it on your worksheet. So starting with equation 1, we have that relativistic linear momentum. And, that's just a plug and chug type question. We know how mass and energy are interconvertible through Einstein's equation. That tells us basically like how much energy is needed to create a mass m or vice versa, right? So that equation of E equals mc squared is basically the amount of energy an object will possess because of its mass. So we know kinetic energy at relativistic speed. That's that whole equation set up. And there's something that I recommend that you do with that equation. Okay. Oh, okay. All right. Sorry, I need to zoom in. Otherwise the handwriting is really bad, so I apologize for it being super large. So that's this equation. Like it might seem obvious, but wait a minute, I messed this up. It might seem obvious, but you need to, I recommend when you do this, you just factor out that mc squared. So that just becomes 1 and that becomes 1. You have mc squared out here, just because I'll save you time when you're plugging everything in, because these variables can be pretty small, very large, it could all fluctuate. So that's just a little tip right there to save time. And then we have a photoelectric effect, which is basically like when you have a light and it shines on a metal surface. You can imagine that the electrons are on that surface are being kicked off, and then that's what the photoelectric effect is. It happens with everything, but like it more is easily visualized with metals. We have the Planck-Einstein relation, and that's basically the energy of a photon. Where we have E, which is energy, H is that Planck's constant, and F equals frequency. I don't know if he updated the formula sheet, but I know he didn't have that constant on there. So I know another student said they were going to email him about that. So if it's still not there, I don't know, maybe bring it up again. And then we have the wavelength of a particle. And we have the equation for an electron jumps from a higher to a lower state. And we can calculate the energy there. We know the angular momentum of an electron through Bohr's model. And we know the energy levels of the Bohr model. Okay, and then the only other equation that I really want to talk about is for that last one, number 8 there. So that's basically just how you find the energy of any orbit, right? So depending on which way you're going to solve, you're either going to solve for the positive or it's going to come out at the negative, to do that conversion to a positive. So yeah, so I think we should just start off with question number 1 here. So we're asked to solve.
Question, Sammy?
Yeah.
About.
Okay, so back to question number 1 here. We want to compare the momentum of an electron to its classical value when it has a speed of that number in an old TV versus when it's 0.8 the speed of light, 0.98 the speed of light in an accelerator. Okay, so here, what are we solving using? We're going to be using the momentum equation. And I got a question of like, oh, when do I use like the classical equation of momentum versus the relativistic one? Basically, if you're at 0.1 times the speed of light, you should use the relativistic one. So, in part A here, let's call this 1. Part A, we know the speed, 4 times 10 to the 7. We know the equation for relativistic momentum. It's that mv divided by 1 minus v squared over c squared. Okay. And we're just going to plug everything in. They give us the velocity, so you just plug in that velocity. You should know what the speed of light is. And then we can leave it in terms of mv actually, just because we're going to be solving in terms of that classical, right? So we're going to make a comparison against the classical. So when you plug in the velocity, what's going to come out is 0. That velocity again, 4 times 10 to the 4 times 10 to the 7, 1.01 mv. Okay, and then the point of leaving it in terms of mv right here is it allows us to make a comparison to what it would have been if we solved it classically, right? Because we know momentum is typically P equals mv. So here, we're basically 1% increase of had it would have been if we used like the classical, right? So the same logic is going to apply to that part B, where in part B, we're going to plug in everything the same, work everything out. So P equals MV. All right, I'm sorry. That should be C, and the square is out here. And we'll know that that C will cancel out and that C squared will cancel out. And the only thing I want to be mindful of is down here, after you do that cancellation down there where it's circled, it's still 0.98 squared. Like, don't get rid of that squared. I know that's a common mistake, and it's just like a quick mistake you'll just make without really thinking about it. And this comes out to be equal to 5 MV. And again, leaving it in this context tells us that an electron that's going at 98% the speed of light has a momentum 5 times that of its classical value. So that's why if you didn't solve this using the relativistic equation, you would have been off by a factor of 5. So that's just to remind you that, you know, when we're at 0.1 C, you should solve using relativistic. Okay. Let's pause here and take questions. Question number 2 now is we want to calculate the kinetic energy and the momentum of a proton traveling at 2.13 times 10 to the 8. So our kinetic energy equation, you know, we talked about this one before, and I already told you what I like to do to save a little bit of time, which is just factor out that MC squared. And what we're left with is this. Okay. And then, you know, we have to remember what's the mass of a proton. 1.67 times 10 to the minus 27. And we're going to multiply that by speed of light squared. And we're going to multiply all of that business by 1 over square root of 1 minus 2. 10 to the 8 squared. And then minus 1. Okay. And then that all comes out to be 6.313 times 10 to the minus 11 joules. Okay. Kinetic energy. And now we want to calculate the momentum. So that's going to be using the same equation as above, you know. We've gone over how to solve that one. And you'll just plug into the equation, work it out through and through. And the answer for the momentum is P equals 5.05 times kilograms meters squared. Okay. So question 2, again, application of equation. All right. So question number 3 now, we have a spacecraft of that mass, and it's accelerated to 0.11 C. We want to know how much kinetic energy does it have? And then if we use the classical formula for kinetic energy, by what percentage would you be error? So basically, solve for kinetic energy using relativistic parameters, using classical equation, and then we're going to find the percent error, like had you incorrectly used the wrong one, right? So calculating kinetic energy, same thing what we just did in the previous one, where I'm going to factor out that MC squared, plug in the mass and the speed of light. So I'm going to say K is equal to 1.8 times 10 to the 6 kilograms times 3 times 10 to the 8 squared, and then times 1 over the square root of 1 minus 0.11 squared minus 1. This whole thing comes out to be equal to 9.89 times 10 to the 18 joules. Okay. And then in part B, remember our equation for a classical kinetic, I'm going to call it KC. Classical kinetic energy equation is 1/2 mv squared, right? So plug in everything, and what you're going to get is 9.8 times 10 to the 18 joules right there. And then if we remember how to calculate percent error, K minus KC over K times 100, that's going to be equal to, I'll just write it in to make the point that I'm trying to make, which is, in this case, is actually pretty similar, just because, remember I said that threshold for relativistic is 0.1 C, so it's just 0.11 C, so it's like pretty close. But had it been any greater difference, you would have seen like an extreme jump between these two values. And it should be around like 1%. So I think it's like 0.9%. Okay. All right. So continuing on here, we want to calculate the energy. Continuing on with question 4, we want to calculate the energy of a photon of blue light, right? So we're given the wavelength here, and we want to report the answer in EV. So you have to remember that a photon has energy E, which is equal to HF, right? So we'll say photon has energy E, which is equal to HF, or that's that Planck constant times F. And if we recall our past lectures, we'll know that F, so where F is equal to C over the wavelength, right? So now we can manipulate this equation such that E is equal to HC over lambda. And again, we're solving for that energy of the photon. So all we have to do is plug in, Planck's constant, 6.63 times 10 to the minus 34. And that's in units of joules times seconds. And then the speed of light, 3 times 10 to the 8, that's meters per second. And then lambda, which is, a measurement of the distance there, so meters, right? So our units come out to be joules, 4.4 times 10 to the minus 19 joules. But oftentimes they ask that we report these values here, like the energy of a photon, of an electron, or what have you, in EV. So we need to do that conversion where 1 EV is equal to 1.6 times 10 to the minus 19 joules. So in this case, we'll just divide by 1, or multiply by 1 over 6 times 10 to the minus 19 joules. Those guys will cancel out like that, and then you'll be able to work the whole thing out. Okay, and then when you do that, that comes out to be equal to 2.8. All right. So sometimes they'll ask for that conversion. I don't know if that's on the formula sheet either, but also maybe a good one to ask, because unless it seems like something he's never gone over before, but that does come up. Okay, so moving along to question 5. We want to calculate the momentum of a photon whose wavelength is 4 times 10 to the minus 7 in part A. And then in part B, we want to find the speed of an electron having the same momentum as the photon in part A. So again, to calculate the momentum of a photon, let's use this equation. We know Planck's constant's given. We know the wavelength of this photon. So, you just have to plug everything in. P is equal to 1.66 times 10 to the minus 27 kilograms times meters per second. Okay. And then we have the momentum of an electron, as we just found, where we know momentum is equal to, P is equal to mv, right? And what we're solving for is that v, right? But we're not going to consider an electron. So we're going to rearrange this equation. So where v is equal to P over m, and that's, mass of electron, the P value, that momentum we just found, so that's going to be equal to 1.66 times 10 to the minus 27 divided by 9.1 times 10 to the minus 31. And that's going to come out to be 1.82 kilometers per second. Okay, so all that is to show that we have that equation, right? That it's like de Broglie's wavelength of a particle equation. And you have to remember, there's a lot of power in how you can manipulate that equation to find velocity of something if you know the momentum, right? So between his equation, which is this, and knowing what momentum is, you can also solve for mass and velocity. So yeah, you just remember to keep that out in mind as long as you know that p value. All right.
I have a question for the
Yeah.
momentum of a photon.
Okay, so in question 6, we have a hydrogen atom and has an electron in the fourth orbital. So we want to know how much energy is needed to ionize it, right? So energy in electron volts, so EV, right? I call it, it's electron volts, required to ionize a hydrogen atom is equal to En minus 13.6 EV divided by N squared, right? And what's that En value? That's just that's just the energy required to ionize an atom of hydrogen by removing that electron from that orbital. So in this case, it'd be that fourth orbital, and it's at that fourth energy level, right? So, plug in 4 here, and you'll solve for En, and En will come out to be 0.85 eV. So, the energy needed to ionize a hydrogen atom with an electron in the fourth orbital is 0.85 electron volts. Okay.
Do we just take the absolute value of it? Because isn't the bottom always going to be positive?
Yeah, so I was going to ask if you made a comment on that in lecture. Like here you're importing like an amount of energy, so you would report it as the positive. In the other cases, like if you were like, what energy, what orbital level is it? They'll provide you the energy negative, so the negatives cancel out. But did he make a comment on if you're going to be reporting it always as a positive or not, or in lecture?
No, I don't, at least I don't remember. But like he gave us that negative equation, the same one that you wrote. So I assume it's like the same thinking.
Yeah, so then I think that that's kind of the point he's trying to get at here. But if you'll look at like in the second one, I mean, okay, so number 7, right? We'll see how it works out nicely in this case. So here we want to consider a hydrogen atom, and it's in the energy state of minus 0.27 eV. In the Bohr model, what is the angular momentum of the electron in the atom with respect to an axis at the nucleus? Sorry, my screen keeps turning off and on, so it's nice and distracting. So again, we know the nth energy state here is equal to minus 0.278 electron volts. And our equation for angular momentum, NH over 2 pi, right? And that's pulled from the angular momentum for an electron by Bohr, which is, L equals mv r n, and then where that Rn is going to be equal to that, it's that centripetal acceleration. So you have to modify the velocity and all that business. And you end up getting L equals NH over 2 pi. So that's when you're trying to find the angular momentum of an electron moving around that molecule. Okay. So, and then H is Planck's constant again. So we have this equation. We have this. Here, let me write this. We have this En value, right? But we need to solve for which orbital we're using. So if we recall, En is equal to minus 13.606 eV over N, where we don't know N, but we know this guy right here. You can just rearrange the equation to solve for N in the following way. And then these negatives will cancel out, and N will come out to be equal to 7. Okay. So now we have N. We can plug that in right here. So L equals 7 times Planck constant, 6.63 times 10 to the minus 34, divided by 2 pi. 2 pi. L is equal to 7.37 times 10 to the minus 34. Okay. All right, and then kind of what I was saying is here we know what the energy is at that state. It's reported as the negative, but here the negatives cancel out. So I think that, well, you know what, I'm going to clarify with him and we can go from there. Or if somebody else clarifies with him before I do, if you email me, I'll post it on the key what they say, but it can kind of either cancel out, or you know, you're presuming you're adding the energy in, so you can consider it as such. Okay, so let me take questions on that.
I just had a question, like, so the any,
Yeah, sorry, someone just brought to my attention. There's the square down there, right? Don't forget that square value. Okay.
I have a question.